Welcome to today's session on design against fluctuating load, stress concentration factor. In this session, I will explain what do you mean by stress concentration, what are the causes of stress concentration, and how to reduce stress concentration, and what do you mean by stress concentration factor. Learning objectives of the today's session. After this session, you will be able to explain stress concentration and its reduction methods. Then you will be able to define fluctuating stresses and how machine components are going to fail against fatigue load, that is fatigue failure. In many industrial applications, you will find components are subjected to varying loads, such as here the mill which is shown, which is also subjected to varying load. Another one is the all-terrain vehicles or all vehicles. You will find because of change in acceleration, speed or braking action are subjected to dynamic loads. That means load does not remain constant, it is going to vary. And because of that, more than 80% of the components are going to fail because of fluctuating or dynamic or varying loads. But why we want to design against fluctuating load? In design against static load, in earlier sessions we have seen elementary equations are used. Now suppose how to find out the stress by using simple elementary equation, the force upon area, so you will get the stresses. Another equation, how to find out the bearing stress, MBY by I. Third one is how to find out the torsional shear stress, the MTR by J. That means by using this elementary equation, we are going to find out the stresses when components subjected to static load condition. But in varying load condition, if you are going to use this elementary equation, you will get some magnitude of the stresses. But because of this varying load condition, the magnitude of the stresses are going to change. That's why this magnitude is going to change? Because in actual practice, discontinuities or abrupt changes of the cross section are present on machine surface or machine element or components, and this is due to oil holes, grooves, keyways, splines, screw threads, soldiers or fillets, steps are provided. All these are the discontinuities, and because of this discontinuities, what is happening? The stresses induced are component which are far higher than the stresses calculated by using the elementary equation that we have already used in design against static load. And therefore, and while designing the components against static load, while taking the area, we are assume the uniform cross section area. But in actual practice, because of these discontinuities or abrupt change in cross section or geometry, the area is going to change, or we can say in another way, elementary equation doesn't give the correct results. This is one of the reasons. Second one, we have assumed the component which is made of homogeneous material. Again, because of this oil holes, grooves, keyways, splines, or sometimes foreign particles or internal cracks or air bubbles in the machine or materials, because of that also the material is also non-homogeneous also. This is also the another reason, and because of that elementary equation doesn't give the correct results. This is one reason. Second one, look at this here. This is the simple plate which is subjected to tensile force F, is having a hole here at the center. Now because of this hole, the geometry, after change in the cross section of the plate, if there is no hole, and if it's a width, it's a length, and this plate is having some thickness T, at that time the area we are going to take W into T is the area. But because of this hole at the center, area of this, if we are going to find out the stress induced in this component, sigma is equal to force F upon area. But by using elementary equation, area is this W into T only here at this cross section. But because of the hole, this area is going to change, or because of this discontinuity or change. So what is going to happen? You will find at this area portion, look at this here, you will find the intensity of this stress magnitude which is maximum, or stress which is maximum at abrupt change at this section. Here again you will find the intensity of this stress is also more, but here it is less. That means localization of high stresses due to irregularities or abrupt change in cross section or geometry. This is known as stress concentration. So what do you mean by stress concentration? Localization of high stresses where at irregularities or abrupt change in cross section or geometry. But in actual practice, by using a simple elementary equation, we are assume cross sectional area is uniform, but that's why it doesn't give the correct result. But here stresses are more. That means at whole magnitude of this localized stress far greater than the stresses obtained by the elementary equations. This is one thing. That's why the simple elementary equations are not feasible directly to use to find out the stresses induced in the component which are subjected to dynamic load. This is one thing. Therefore, what we have to do? We have to, it becomes necessary to modify the stresses which are calculated by simple all elementary equation. And how to modify these stresses? Because at the abrupt change or where the geometry changes or the section changes, the intensity of that stress is more. To take into account that the changes or change in stress magnitude, what we have to do? We have to introduce here stress concentration factor. That means to account for this effect of stress concentration, the stress concentration factor is introduced and it takes the care of this, the modified stresses or localized stresses because of the abrupt change in geometry or cross section. So what do you mean by stress concentration factor? The stress concentration factor means it is the ratio of the highest value of stress. Look at this, because of this whole, here you will find highest value of the stress. Look at the cursor, highest value of the stress magnitude. This is because of this abrupt change in cross section divided by or upon the normal stress determined the elementary equation for minimum cross section. So therefore, the stress concentration factor which is denoted by Kt, the Kt is equal to sigma max by sigma normal. That means it's a ratio of maximum stress near the discontinuity upon sigma normal. Sigma normal means which is calculated by using elementary equation. Now let us take this example. This plates having a hole. So now what is the normal stress? Force upon area. What is the area? W minus D into T. D is the diameter of that hole which is here. Look at this. This is the diameter of the hole D. So you will get this. So you will get sigma normal here. You can substitute here this. And what is the sigma max? So you will get sigma max here at the localize here where the change in cross section. So you will get the maximum stress. The max upon sigma normal you will get the Kt, or you can say sigma maximum. So how to calculate the maximum magnitude of stress because of stress concentration, or you can say stress concentration means change in geometry, that is sigma max is equal to Kt into sigma normal. Sigma normal by elementary equation and Kt is stress concentration factor. So by using this expression we can find out Kt or sigma max also. What are the causes of stress concentration? Now here variation in material properties. But here while using the same in static load condition we have assumed material is homogeneous one. But in actual practice it's a non-homogeneous material. That means cavities are present, here holes are present, internal cracks to the material, some foreign inclusion means another content of the material in material. And because of that the material properties are going to change, and it is one of the reason it also induces the stresses in it. This is the stress concentration. Then second one, load application. Now forces or load which acts at a point over a small area. In case of gears, bearing, cam and follower, you will find there is a point contact, and because of this you will find because of this point load it acts over a small area. That means while calculating the stresses by using elementary equation we are considering the small area, but that time you will find pressure is more in case of gears also, in case of cam and followers also, in case of ball bearings also. And because of this also what is going to happen, there is a stress concentration at the localized area where this point load which acts. That's why load application is the another cause of stress concentration. Then third one is the abrupt change in section. Abrupt change, let the example of here shaft. Now to mount the different parts, that is pulleys, gears or sprockets on the shafts, again you will find shafts are here given the steps to the shafts of different diameters, and because of these steps or fillets are provided because of these steps where there is a change in cross-sectional area of the shaft, and because of this changing cross-sectional area where you will find the intensity of this stress concentration is more. This is also the another cause of stress concentration, that is abrupt change in geometry or cross-section. And the last one, discontinuities in the component. Discontinuities in the component, take the example of a shaft. To mount these gears or the pulleys on the shafts, that means to prevent its relative motion or movement, keys are used. And to fit properly key on the shaft, keyway means slot which is provided here. That means it removes the material of the shafts. That means discontinuity in the component. Similarly, oil holes in case of the bearing housing or the bush to supply the oil hole which is provided. Again, on spline shaft you will find the splines are provided. That means there is a abrupt change again because of these discontinuities, abrupt change in the section, and all because of this the stress, there is a stress concentration. Now here it's okay. You will find more than 80% of the components are going to fail because of dynamic load condition, and main cause is the stress concentration or intensity or magnitude of this stress concentration. But how to determine this stress concentration factor to take into account while designing the components? There are two methods. One is analysis or analytical method based on theory of elasticity. And second one is the experimental method, that is photo-elasticity method. But by using this numerical or analytical method based on the theory of elasticity, you will find, suppose the rectangular plate is having a circular hole and subjected to tensile force which is shown in earlier slide, and if by using the analytical method based on theory of elasticity, you will get here the KT, that is stress concentration factor, is equal to 3. But in this case small circular wall. But in actual practice you will find this, the geometry of the components which is somehow complicated or complex shapes are there, and because of that it becomes very difficult to use this analytical method based on theory of elasticity to find out the KT, and it's a time consuming laborious task, and again lot of calculations are involved to make the analysis for the complex shapes. That's why there is another method, that is photoelasticity method. Now here in photoelasticity method, here it's a visual method in which full field stress distribution in a photoelastic material which is observed directly. That means here samples of the machine components are made by using this elastic material, and which is subjected to load, and in laboratory the Polariscope which is used. Now here is the observer, again here polarizer, or this is also the analyzer, and this is the light source. Now in this case light source, when it is passed to the polarizer, because of the transparent material which is used for this model, through this, and when it is subjected to the load, there is a arrangement of loading also. Observer can observe the distinctive colored fringe patterns, and interpretation of this pattern reverse the overall change distribution. You will find by using this photoelasticity method or Polariscope, you will find the, suppose if you would like to have a different, the change in geometry or the cross section, accordingly different models are prepared in laboratory, and laboratory test which is carried by using this Polariscope, and different fringe patterns are obtained for different shape and sizes and geometries. And you will find these fringe patterns are in this fashion, and this interpretation gives the straining, the where you will get the maximum stress concentration, straining or deformation of the components. This is about the automobile connecting rod, or it's a laboratory method. That means because of changing cross section, now here cross section is going to change here. So because of that, what is this stress distribution or the strain pattern or the pinch pattern? Accordingly, for different components, by using this method, different pinch patterns are obtained, and based on that, the R.E.Peterson, who is carried out this laboratory method for different cross sections or geometries which are subjected to tensile, torsional and bending loads, and based on this laboratory test or a photoelasticity method, the many charts, R.E.Peterson charts are available in data books to take the value of KT, because it's a time consuming and laborious, the task. But R.E.Peterson's done lot of, the experiments by using this method, and these charts are available to us directly to take the value of KT. Now here you will find this is the geometry of the machine element having small is subjected to P means tensile force. Look at this, these are subjected to tensile force having diameter small d, capital D, and here on x-axis you will find small r by small d. So you have to take this ratio here, and again here capital D by small d, different lines are given here, and y-axis here KT, that is stress concentration. That means you have to take r by d. If your geometry of the machine element is like this, subjected to tensile force, find out r by d, and then what is capital D by small d, you have to select that line and find out the value of KT. That means by using R.E.Peterson charts, again you will get the value of KT. This is one way to get the value of KT. Then second, here also the same machine element but subjected to torsional moment. Again for that different, that means in laboratory different loads applied on the machine elements, and accordingly here the charts are plotted to get the value of KT, and these charts are available in many data books. Again here you will find the component which is subjected to bending moment, here torsional moment, and you will get the different values of KT. That means the varying load or the load condition also, so you will get the, even though dimensions are same, but here axial load, tensile load, torsional moment, bending moment, you will get the different values of the KTs. That means by using R.E.Peterson chart, you will get directly the value of KT. Now, when and where to consider the stress concentration factor? As already discussed in earlier slide, stress concentration depends upon the material of the component. And under static load, what will happen? Ductile materials are not affected by stress concentration. Now again, try to understand, while designing the component, there are two criteria. One is the static, another one is the dynamic. In static, again, whether the component is made up of ductile material or a brittle material. If it's made up of a ductile material, no need to consider the stress concentration. Why? Because when the stress concentration at the discontinuity reaches at the yield point, imagine your strain curve, you will find when it reaches to the yield point, that time plastic deformation starts, and when plastic deformation starts, you will find it results in redistribution of the stresses, and because of that, no need to consider the stress concentration in case of ductile material when subjected in static load condition. Try to understand. That means under static load, when ductile material is used, no need to consider stress concentration factor. But another case, in case of brittle material, when subjected to static load, so you will find the effect of the stress concentration is more, and there is no plastic deformation due to any ability of the plastic deformation of the brittle material, and because of that, there may be the sudden failure of the material or machine components. That's why we have to consider the stress concentration in case of brittle material subjected to static load. And third case, when component is subjected to fluctuating load, dynamic load, varying load, that time we have to consider the stress concentration factor even though material or component which is made up of ductile material. Try to understand. That means in static case, material is ductile, no need to consider. In static case, material is brittle, consider stress concentration. And second case, dynamic load condition or fluctuating load condition, material may be ductile or material may be brittle, we have to consider stress concentration factor. And why? Because of these fluctuating stresses, you will find magnitude of this endurance strength or fatigue strength, it may be or you will find component may fail before reaching to the ultimate tensile strength, or in some times may before, or it may fail before the yield stress also. That's why it's necessary to consider in case of fluctuating lead for both the cases made up of ductile material as well as the brittle material. That is important. But how to reduce the stress concentration effect? It's not possible to avoid discontinuities or abrupt changes of the cross section, because which is the requirement for proper mounting of the elements of the mechanical system. And because of that, it's not possible to reduce this, avoid the stress concentration. But what we will do, we can reduce the effect of this stress concentration up to certain extent by selecting correct geometry, and second, it can be reduced by using principles of minimization of the material. There are basically three methods. First one is the use of multiple notches, second one is the removal of undesired material, and third one is the drilling of additional holes. By using these three methods, we can reduce, or it's possible to reduce the stress concentration effect in machine components. Let us see. Now here, this is the plate is having the notches here. These are the stress lines. The intensity of the stress you will find at this portion, which is high. But how to reduce it? That's why first method is by multiple notches. So instead of having a single near to this here, notches are provided here. And because of that, what is happen? The intensity which is abrupt because of this notch, which is higher, it gets reduced here. You will find it becomes uniform here in this case. This is one case. Second one, again by drilling holes near to the notches. Instead of having the multiple notches, by drilling hole also here, the intensity gets reduced, or magnitude of this sigma max gets reduced. That means stress concentration get reduced. And third one, by removing this notch here, this material, so directly, the head section, this material which is removed here from this, again though it also reduces. That means by multiple notches, one option, second by drilling hole, and third one is the by removing the material. Again, because of this, again you will find in case of the shaft keyway is present, that time because of this keyway you will find the stress concentration at the keyway part, which is the more. But how to reduce it? You can drill from both the sides towards that keyway. You will find the intensity or stress concentration get reduced by drilling the hole. That means by multiple notches, drilling holes and removing material, we can reduce it. Then again here we have seen in earlier session also design for strength. In design for strength, test and diagram curve, you will find SYT or SUT is the criteria, and component is going to fail here and when subjected to static load. But when component is subjected to dynamic, cyclic or unsteady load, you will find component which is designed for a life may be infinite life or a finite life. We will see in next session how to design the components for fluctuating load conditions. But try to understand two criteria. One is SYT, SUT, in this case designed for finite or infinite lives when subjected to dynamic load. What do you mean by fluctuating stresses? In many applications, as I have told, force or load which are not static but vary with time, and the stresses induced are called or known as the fluctuating stresses. That means when components subjected to varying load, because of that stresses are gets induced, and these stresses are known as fluctuating stresses. So you will find more than, I have already told, more than 80% components fail because of this, and you will find this stress variation because of this varying load which is irregular and unpredictable. We can't predict. Because of that, component may fall before reaching to SUT or before reaching to SYT also. And to make the design analysis, simple model stress-time relationships are used, and popular model of stress-time relationship is sine curve. We will see in next session about the sine curve. Then again, what do you mean by fatigue and fatigue failure? When components subjected to fluctuating stresses, so what is going to happen? Component may fail. Sometimes it may fail when stress magnitude which is lower than the SUT, or sometimes even smaller than the SYT. That means as the time passes, when subjected to varying load, the magnitude of stress causing the fatigue failure decreases as the number of cycle increases. That is important. Magnitude of stress causing the fatigue failure decreases as the number of stress cycle increases. Number of stress cycle means how many number of the RPM cycles or million revolution that component can sustain, and it is going to decrease as the number of cycle increases. That means this phenomena of decreased resistance of the material to fluctuating stresses is called fatigue or fatigue failure. The phenomena of decreased resistance of the material to fluctuating stresses is called fatigue. That is important. Try to understand and remember this. Now I have covered in today's session what you mean by stress concentration, its importance in design against fluctuating load, what are the causes of stress concentration, how to reduce stress concentration, what do you mean by fluctuating stress, and what do you mean by fatigue failure. Some the questions for recap. What is stress concentration? Because of abrupt change, geometry, change in shape, size at the localized point, high magnitude stresses, that is stress concentration. Then second, how will you account for stress concentration in design? By considering the stress concentration factor KT, and KT is equal to sigma max upon sigma normal. Sigma normal you will get by elementary equation, and sigma max is the magnitude at the localized point where there is a abrupt change. What are the causes of stress concentration? I have already told. That is material properties, non-homogeneous material, then load, then abrupt change. All these are the reason. Then what are the methods of reducing stress concentration? By multiple notches, second by drilling holes, and third by removing the material. Now what is fluctuating stress? When components subjected to varying load, stresses induced in it is called fluctuating. And what is fatigue failure? Component may fail before SUT or sometimes before SYT also. And what do you mean by fatigue? The phenomena of decreased resistance of the material or a component to fluctuating stress is known as a fatigue. If you have any query, you can contact me at 989042669 or mail me at pbkushar@kkwork.edu.in. Thank you. I have read per vendor is book design of machine element, third edition, McGraw-Hill publication.